So in our last classes, we learned about first the applications of microwave engineering and where it is applied. Then we learned about how electromagnetic waves propagate in the space and in media, and what are the main characteristics of such kind of waves, and the parameters that are used to define such waves. Also, we learned about Maxwell's equations and how we can understand the propagation of electromagnetic waves using the Maxwell's equations. So today we will be talking about the transmission lines. So transmission lines are used for transmitting information from one end to another. And specifically, we are talking about high frequency data transmission in this module. So microwave range is in high frequency, like in gigahertz region. So therefore, we have high frequency data transmission and high frequency wave propagation. So currently we are in the second title of the module. So that is the transmission lines and impedance matching. So from today, we are starting the transmission lines and theory behind it. And next we will learn about impedance matching. That means how we can connect, for example, transmission lines to loads, and how we can minimize the energy loss when we connect the transmission lines to a certain load. So once we connect a transmission line to a load, some energy is getting lost because of the reflection that can happen at the connection area. So we will talk about those things after transmission lines. So I mentioned this earlier. So in electromagnetic wave propagation, there are three types of propagation. So the three types are TEM mode, transverse electromagnetic mode, where electric and magnetic fields are perpendicular to the direction of the wave. And the second type is transverse electric mode, which is like electric field is perpendicular to the direction of the wave propagation, and the magnetic field components are existing along the direction of the propagation. And third type is transverse magnetic. That means the magnetic field is perpendicular to the direction of the wave propagation, and electric field components are along the direction of the wave propagating. So these are the types of electromagnetic wave propagation that can happen in circuits. So in this transmission line section, we will be focusing on transverse electromagnetic mode of propagation. So what is a transmission line, right? Transmission line is basically a two or more parallel conductors with insulating material in between. So we can take, for example, a PCB circuit where we have two conductors, the top conductor and the ground plane, or the bottom conductor. So in PCB circuits, we have transmission lines which are like microstrip lines or strip lines that can that is the top conductor, and then we have the bottom conductor, which is the ground plane, which is spreaded over the entire PCB board. So the top conductor is kind of a thin connection line. However, the bottom conductor is a wide transmission line. So therefore, I mean, the width of the top and the bottom conductors can be different. However, they are transmission lines with a voltage difference between them, and there's a dielectric material in between them. So in PCB circuits, we see lines like this. So these are the top conductors. And once we look at the ground plane, there's a ground plane all over the total area of the PCB circuit, right? And then we can consider that the physical dimensions of these kind of circuits are almost similar to the um, wavelength of the wave that is propagated. That means that the physical dimensions of the circuit components are in millimeter, centimeter range. And also we know that the wavelength of the microwaves are in millimeter and centimeter range. So the wavelength of the microwaves are almost closely equal to the physical dimensions of the components in the microwave circuits. So therefore, when we are designing microwave circuits and when we are fabricating them, we need to be accurate with the dimensions, because if there's a reduction in the precision, the performance that we expect from the circuit might not be achieved. And therefore we need to understand that the precision of the dimensions of the circuit components are very important in microwave circuits. And these microwave circuit dimensions determine the capacitance, inductance, resistance, conductance of the transmission lines and the circuits. So those circuit parameters are generated using the dimensions of the components that we use. So therefore, we determine those capacitance, inductance, resistance, and conductance using the dimensions of these components. And therefore, when we design these circuits, we need to be extremely considerate about that. And once we take the examples of transmission lines, we can take PCB circuit boards, as I mentioned before. So in PCB circuit boards, we have different types of transmission lines. So we have this microstrip line, right? Microstrip line is this line where we this horizontal, this piece of metal strip, which is used to input or feed a certain signal, and then it is used to, this transmission line is used to carry the signal from the input source to the antenna. So this is a real picture of such a implementation. And so when we take the top view, it is like this. When we take the side view, it is like this. So there's a dielectric medium between the two conductors, and the ground plane is spreaded all over the PCB board. And then we are using these kind of situations to supply power to antenna and so on. So in microstrip line, in this example, the power is supplied and to the transmission line, which will provide power to the microstrip antenna. So this is an antenna. And then we also can take coaxial cable transmissions. So in coaxial cables also, we can transmit high frequency signals. So in the range of, we can take in the range of kilohertz, megahertz, and then up to gigahertz. However, we also need to keep in mind that coaxial cables are not much used for gigahertz range of communications. However, for some applications it is used. Coaxial cables are used for multiple applications, not only for the microwave applications. So it is used for transmitting data, internet and video, video and voice communications. It is consisting of two coaxial conductors separated by an insulating electric material. So the inner conductor is a copper wire, the outer conductor is a copper mesh, and there's an insulating material in between the conductors. And then we have an outside insulation which will surround the total the total coaxial cable, and they are made of plastic or some kind of insulating material which will prevent any damage to the coaxial cable. So the dielectric insulator is used to minimize the signal loss. Next we are going to look at how we can model a transmission line using circuit parameters, right? So in order for us to understand the performance of wave propagation in a transmission line, we look at how we can mathematically model the transmission line using the components, the circuit theories we know. So we take into consideration the effect of the current and the voltage flowing across the transmission line, and by considering that we consider different components for the transmission line, and using that we are defining a circuit for the transmission line. So once we take a transmission line, we can consider that we are considering a uniform transmission line. So what I mean is that once we are considering transmission lines, we are considering the uniform transmission line, and that means that each cross section of the transmission line is equal at all points. Once we take the top conductor, it could be of a different width when you can compare to the width of the bottom conductor. So the top conductor could be having a lesser width than the bottom conductor. However, the top conductor's width will be uniform throughout the transmission line, and then the bottom conductor's width will be uniform throughout the transmission line. So we are considering such kind of a transmission line, and the dielectric thickness will be constant throughout the transmission line. And then so we will first consider the phenomena that happens due to the the imperfection of the dielectric material. So once there's a transmission line with the dielectric material between this top conductor and the bottom conductor might not be perfect. Because of that, there could be some stray currents that are conducting across the two conductors. So because of that, a voltage is produced between these two conductors. So in order to show that phenomena, we denote the stray current leakage using using a resistor. So the resistor is added in between the two conductors, and it is used to denote the stray currents that are leaking from the top conductor towards the bottom conductor, and it is because of the dielectric imperfection. So therefore, we first introduce a resistor to the transmission line circuit, right? So once we take any point in the transmission line, we can denote this resistor in that point. So Likewise, we consider a certain cross section of the uniform transmission line, and we denote the circuit component for that specific cross section of the transmission line. So first, we denoted the stray currents using the resistor. Next, we denote the voltage that is generated across this resistor using a capacitor. So the stray capacitance that is generated is denoted using the capacitor that is in parallel to the resistor, right? So the capacitor will denote the capacitance that is getting stored because of the voltage that is created across the resistor that we denoted earlier. So the resistor is added because there is a stray current that is flowing across the dielectric medium, and therefore there's some resistance between the two transmission conductors. Then once we take into consideration the input current that is fed to this transmission line. So when we take the current coming from the left side, we can take the current coming from here. We can take it is inducing a magnetic field in the conductor, right? In order to show the magnetic induction, we are denoting the induction using an inductor in series to the current propagation, and therefore we add the inductor. So so far, while after taking a cross section of the transmission line, we have the inductor, parallel resistor, and parallel capacitor. Next, we consider the last component that is added to the circuit. So once we consider a conductor, the conductor can be imperfect due to the resistance inside the conductor. So so in real world, the conductors are not perfect. So because of that, we need to add a resistor to denote the imperfect conductor and the leakage current that flow because of the imperfect conductor. So we add the series resistor to denote the leakage current due to the imperfection of the conductor. So so in summary, we have added a series resistor because in order to represent the imperfection of the conductor, and then we have added the inductor in order to show the magnetic induction due to the current that is flowing across the metal wire. And then we have added the parallel resistor to denote the stray currents that are flowing from the top conductor to the bottom conductor due to the stray currents that are flowing across the imperfect dielectric material. And then we introduced a capacitor to denote the voltage that is getting stored between the two conductors due to these stray currents that are flowing through the dielectric medium. So we have now defined the circuit for the transmission line using circuit components. So now we can define a small cross section of the transmission line using this circuit, right? So this circuit can represent any cross section of the transmission line, and it will enable us to understand the behavior of a delta Z length of a transmission line, and from that we can predict the behavior of the rest of the transmission line components, and use this as the like basic element of the transmission line. So this is the basic element of the transmission line, and we have denoted it using a circuit representation. So once we have develop some mathematical equations related to this, we can find out the relationship between the voltages and currents and the resistance in the transmission line. So now we have in this diagram denoted the voltages and the currents in the circuit. So the voltage, input voltage at the position Z at time t is denoted by V ZT, and the current is denoted by I ZT at the position Z. And then when we take the voltage and current at the position Z plus delta Z, we take it as these parameters VZ plus delta Z comma T and IZ plus delta Z comma T. So the voltages at the input side at Z and at Z equals Z plus delta Z are actually different parameters. So we need to consider the location also when we denote the voltages and currents. That means we need to consider at what position we are considering the voltage and denote the voltage according to the position of the position in the conductor. So the voltage at Z might not be equal to the voltage at Z plus delta Z. The current is also similar. The current can vary at the position Z and at the position Z plus delta Z. And so when we are defining parameters for the resistors and the values for the resistors, inductor and capacitor and the conductance, we define the value for resistance, inductance, capacitance and conductance per unit length, right? So the capital R here is defined as the series resistance per unit length. This is a series resistor. So the resistance in this resistor is the series resistance, and it is defined, the capital R is defined per unit length. So it is given by the unit omega over meters. And then the inductor, right? The inductance caused by the inductor is given by capital L, and it is measured per unit length, and it is given by the SI units, Henry per meters. Henry per meters. Okay. So we can denote the conductance by capital G, and since it is a parallel conductance, we call this shunt conductance, and the capital G denotes the shunt conductance per unit length, and it is given by the SI units, Siemens per meters. And then the capacitor value, the capacitance is denoted by farads per meter, and this capital C denotes the shunt capacitance per unit length. Then we have, so in transmission lines, I have mentioned that there are two conductors, the top conductor and the bottom conductor. And so we consider that the cross section of the transmission line is similar at each point of the transmission line. So it is a uniform transmission line. So Apart from that, we consider that the electric components are joined by perfectly conducting wires. That means once we have represented the transmission line like this circuit, the total resistance in between these components is almost zero. All the resistance are lumped into this circuit component, right? Likewise, these wires which are connecting the components are known as perfectly conducting wires. And then we have the insulating material between these two conductors. The insulating material is between these two conductors, and the imperfect dielectrics cause the stray currents, and it causes the difference in the voltage and current at source and the load ends, right? So the difference in the voltage at the source end and the load end is because of the stray current that is flowing across the two conductors. So because of that, we lose some of the current and the voltages while the wave is propagating from the source end to the load end. So because of that, the input voltage and the output voltage are different. So there's a voltage drop across the transmission line. So once we take the delta Z cross section of the transmission line, we can develop the relationship between the input voltage and the output voltage using the Kirchhoff's voltage law. The Kirchhoff's voltage law we can apply to a loop inside the circuit, and we can derive a connection between the voltages, and we can simplify and we can find some important equations from the derived outputs. So we can use the Kirchhoff's voltage law as we know, and we can derive equations by taking into consideration the voltage drop through the loop, right? So once we take the voltage at the source to be VZT, we can write that VZT is equal, the voltage here is VZT. Right, so V is at T, we can equal to the voltage across this resistor, which is the current across this resistor into the resistance, the total resistance, right? The total resistance is capital R into delta Z, right? The total resistance into the current gives the voltage drop across the resistor. And then the total voltage drop across the inductor we can take as the inductance value into delta I over delta T, right? So we know that the voltage drop across the inductor is given by the inductance value multiplied by the rate of change of current across the inductor. And then, we multiply that amount by delta Z to take the total voltage drop across the inductor component. And then we have the voltage at the load end, or the opposite, the end of delta Z, that is minus V Z plus delta Z comma T. And once we take the components of VZT and VZ plus delta Z comma T onto one side, we can consider that expression as delta V over Z. Right. So then we can take the values of the terms related to these voltage drops across the resistor and the inductor to one side, right? So I hope you understood that, right? So once we take the parameters of the VZ and we right. So once we take this term into this side and we set t into the right side, we can take the difference between Vz plus delta Z minus Vz t. So that is denoting how much of voltage is changing across delta Z length, right? So Vz plus delta Z minus Vz t is denoting how much of voltage drop is happening across the length delta Z, right? So this, once we take the limit of this expression where delta Z is going to 0, we can write that expression is equal to dabba V over dabba Z. So once Z plus Vz plus delta Z comma t minus Vz t is there, right? So in this expression, this is the expression that you will receive over the right side of this equation once you solve this equation, right? So so once you right, so once you make the delta Z value go to 0, we can say that the this expression is equal to dabba V over dabba Z. Right? So we have sent the delta Z to 0. That means there's a very small difference between the voltage values, and therefore we denote it using dabba V over dabba Z. So delta Z is not equal to 0, it is reaching 0, right? So therefore we can't cancel these two terms and equal it to 0. But there's a certain small difference between these two voltage values. So that small difference of voltage value we consider and we can denote that using dabba V over dabba Z, right? So that is coming from the differential equation principles, and using that we can write dabba V over dabba Z is equal to the voltage drops that occur across the resistor and the inductor, right? So did you understand up to this point? And if you have any questions, you can ask in the chat, or you can ask me in the interactive session class. So if you have any questions, please let me know. And once we consider the Kirchhoff's current law, we can take an expression for the current that is the relationship between currents in this circuit. Then using that, we can find an equation for the current, and we can find out the relationship between the current across the transmission line and the voltage expressions. So using current Kirchhoff's current law, we can write an equation like this. So you know that the Kirchhoff's current law needs to be applied to a node in the circuit. So we can make the total sum of currents that are reaching a certain node in the circuit to 0. So the total current which is reaching this point in the circuit, we can equal to 0. And using this relationship, we can build an equation between the currents and the voltage in the circuit. So when we take the currents that are reaching the node N, we can write the current current that is incoming from the left side is IZT, and then the current which is flowing out is IZ plus delta Z comma T. And then, so therefore we put the minus sign there. And then the current that is going outward from the node N is, because of the capacitor, is equal to the C delta Z into W V over W T at Z plus delta Z. So you know that the current that flows across the capacitor can be modeled using the capacitor value into the voltage drop across the capacitor. So by multiplying the capacitor value with the voltage drop across the capacitor, we can find out the total current that is flowing across the capacitor. So using that, we can find the total current, and then we multiply by the delta Z to find the total current that is flowing across this component. And then we can find the total current across the resistor using by multiplying the conductance value with the voltage value. So we can take the total current by multiplying the conductance value with the voltage value across the resistor. So from that we can obtain the current between the resistor, current flowing across the resistor. So once we have found out the current that is flowing out across the capacitor and the resistor, we can complete this equation that we have formed from the Kirchhoff's current law. And then we can take out the terms which are having the G and C parameters to one side, and we can leave only the current IZT and IZ plus delta ZT components in one side. And then just as before, we can equate the delta Z value to 0, and we can denote the incremental increase in the current using delta I over delta Z. And then we can write it equal to the G minus GV ZT minus C delta V over delta T expressions. So we can find out the relationship between the current and the voltage using this equation. So so previously we have found a similar relationship between voltages and currents, right? So once we take out the two equations that we have formed previously, we can put them in one place like this. So this is these are the two equations that we derived, and these equations are known as telegraph equations. So these telegraph equations were derived by a scientist called Oliver Heaviside, and he used these waves to equations to describe the waves that are propagating in telegraph lines, which were used to communicate telegraph informations in the 1830s and 1840s. So he derived these equations to model the propagation of waves in the telegraph lines. So because of that, these equations are known as telegraph equations. And these equations are also very important to identify the wave behavior of the transmitted waves. So once we consider the telegraph equations, we can consider a special case where we consider the transmission line to be lossless. So once we consider a lossless transmission line, the resistance and the conductance of such a transmission line will be equal to 0. And once we make those resistance and values of the G equal to 0, we can get simplified equations from the telegraph equations. So initially we have these two equations as the telegraph equations, and we can simplify we can make the R and the G values equal to 0, and once we make them to 0, these terms will be 0, and then we can write the equations like this. So dabba V over dabba Z is equal to minus L dabba I over dabba T. And also we can write with respect to the current, dabba I over dabba Z is equal to the minus C dabba V over dabba T, and so on. So once we have these two equations, we are trying to find a relationship between the same parameter. Okay, so we want to know like what is happening to the voltage. So in order for us to find out the voltage relationship and how the voltage is changing, we need to remove the effect from the current. So because of that, once we have the term dabba I over dabba T, we are substituting it with the other equation we have, which is given in the second equation. So we can substitute now, since these two terms are equal, we can substitute the minus C dabba V over dabba T here, and we can remove the effect from the current in these equations. So we have the equation in this manner, and we have only the terms related to voltage. Finally, once we substitute this term into once we substitute this C into dabba V over dabba T term into this dabba I over dabba T, then we get this expression on the right side of the equation. Also, once we consider the situation where now in here we have actually taken the derivative with respect to Z on both sides, right? So once we take the derivative of Z on both sides, we can write the derivative of the current with respect to dabba T and dabba Z. And we can get the same expression for the second equation also, right? I hope it is clear to you. So the ultimate goal is to find the relationship between the second order voltage value with the voltage. The relationship between the voltage in the transmission line, and we want to show that voltage is behaving as a certain wave. So in order for us to get the wave equation, we need to obtain the second order term of the voltage. So because of that, we first take the derivative of this term with respect to dabba Z, and then we equate that to so that will be equal to the dabba I squared over dabba T into dabba Z. So once we take this expression, we can obtain the same expression once we take the derivative of this second equation with respect to dabba T. So once we take this derivative with respect to dabba T, we can take the derivative of with respect to dabba T on the left side, right side of the second equation. So using that behavior, we can equate these two equations, and we can obtain an expression like this. So once we have an expression like that, we can equate that to the classical wave equation in the physics, right? So okay, so once we compare that to the classical wave equation in physics, we can observe that the equation that we derived for the voltages using the previous equations are almost similar to the wave equation in the physics, right? So in physics, we learned that the second derivative of uh, the wave displacement is equal to the first derivative of the wave equation with respect to the time and the current, the wave velocity. So we can take that these two expressions are almost similar, right? So using that expression, we can consider that the voltage is um, performing a certain behavior similar to a wave. So because of that, we can derive the conclusion that the velocity of the wave will be equal to 1 over LC squared. Okay, so the reason is that now in here we actually there should be a square term here and there should be a square term here. So I will explain that again, right? So earlier we obtained this equation, right? We obtained this equation using derivatives, and we have this expression. So in classical physics, right, when we take the wave propagation in medium, we have a certain equation which we call as the wave equation. So this is the classical equation that is used to denote waves in physics, right? Classical wave equation in physics. So that equation is also very similar. It is almost similar to the expression that we have derived, right? So there's a square term of the I mean the displacement of the voltage y with respect to time in both the equations, and in here the derivative with respect to the z is there in both terms. So same uh, same parameters are taken into consideration in both the equations z and t. So so based on z and t, these parameters are varying in both the equations. So the only difference is, I mean, this parameter and this parameter, right? So we have, so these are constant parameters in both the equations. So since these the equations are similar, we can equate these two parameters. We can equate these two parameters, and we can derive an equation for the velocity of the voltage wave in transmission lines using the wave velocity expression in classical wave equations, right? So in classical waves in physics, we define the wave equation using this equation. So in this equation, we have a term called wave velocity, right? So the wave velocity is given by this Vp, and this Vp denotes the wave velocity. So there's a similarity between the second equation and the first equation, uh, we can derive a relationship between LC and the wave velocity by equating these two parameters, because these two expressions, the equation A and equation B, are similar. Therefore, we equate these two parameters, and by equating, we can find that the wave velocity is equal to 1 over square root LC. So that means that we can determine the velocity of the wave that is propagating in a transmission line using the components in the transmission line. So components L and C, we can define the wave velocity of the transmission line. So we can we can actually consider this as a very important equation. This equation tell us that by just considering the components L and C, we can determine the velocity of the wave. From the other, other equations that are related to current, also we can derive the same relationship for the wave velocity. So the same output or the same result for the wave velocity is coming from the relationship between the uh, current wave equation and the classical wave equation. So we can consider the similarity and we can derive the wave velocity as 1 over square root LC for this by using these equations also. That proves that the wave velocity equation is correct. So in both cases, we got the same answer. So we consider that the correct expression is obtained for the wave velocity, right? So one student had asked some question regarding the module exam mark allocation for the module. So as of now, we have decided that we are allocating, uh, I mean, 20% for the mid exam, 60% for the end exam. Um, and for the rest of the 20%, it would be based on lab sessions, assignments, and quizzes. So we are assigning for the lab sessions 10%, and for the assignments 5%, and for the quizzes 5%. So that is how the marks will be allocated for this module. So I hope achieve the you achieve the answers to your question, right? So I hope you are okay with that mark allocation. So we are having both mid exam and end exam for this module. So most of the marks will be given for the end exam. However, in the classes we are conducting, we are actually doing tutorial classes, which give you the guidance to complete the end exam. Yes. Do you have any questions? So for the end exam, we are preparing you for the end exam through the tutorials that we are providing. So most of the time you can actually score marks for the end exam using the tutorial sessions that we are conducting and the questions and answers sessions that we are conducting. So therefore, I don't think there's a difficulty there. So most of the assignment marks and the lab marks will be taken into consideration for the final grade. So the quizzes, if I'm conducting, I will let you know. Otherwise, if I don't conduct a quiz, the total mark will the quiz marks will also be assigned for the assignments. So assignments will be 10%, lab sessions will be 10%. So it is mandatory that you complete the lab sessions in order to get the 10%. So you have, I think, 2 or 3 lab sessions. So by completing them and submitting the lab reports, you need to complete that section and you will be able to get marks for that. So for the mid exam, I need to discuss with the other module owner, and we will decide what we will give you. So it would be either a written exam, or else we will give you some assignment that you can do and then you can submit. So I will discuss and I will let you know how it will be done. So those are the deliverables of assessment methods of this module. So since the time is over, I will end the session for today. So today I was actually going through the transmission lines. So the transmission lines are basically used to transmit energy from one point to another. And basically I explained about the circuit model of a transmission line at a certain cross section that we consider with a length delta Z. So we can denote that small cross section of the transmission line using capacitors, resistors, parallel resistors, and capacitors. So by taking the Kirchhoff's voltage law and Kirchhoff currents law equations of the circuit diagram, I have derived the equations for the voltages and currents across the transmission line. Next, after taking into consideration the lossless transmission lines, the lossless transmission lines will have the resistance and the parallel resistance equal to 0. So in that case, we can we can simplify the equations that we take in the Kirchhoff, by taking into consideration the Kirchhoff's voltage law and the current law. And we can simplify it into a form, and we can show that the voltage is following a wave behavior in the transmission line, and we can derive the wave velocity with respect to the inductor and capacitor value of the circuit. Okay, so I will let you know in advance if there are lab sessions, and currently there are no lab sessions allocated for you. So if if they are starting, I will let you know in the lectures and in the interactive classes beforehand. So thank you so much for participating in today's class. I will end the meeting today. If you have any questions, you can let me know.